Okay, welcome everyone. So Suresh will continue with this third session today. Okay.
Okay, thank you. Okay, so yeah, unlike the last two times, this time I have not been able to prepare everything before the lecture. So half of my lecture is prepared and the other half I will scribble during the lecture. Also, as I realized, yeah, I've been trying to cover the basics of scheme theory and cohomology, starting from varieties, and it takes quite a bit of time. And uh, so I'm not sure. I mean, I certainly cannot hope to cover everything. Of course, I've been skipping a lot of details, but even then, I think I have to skip more details. And so today I'll be a bit more sketchy. And I hope I will get to talk a little bit about Serre duality in the second half of today's lecture. Okay, so last two lectures. First lecture we talked about varieties and I mean affine projective varieties and sheaf of regular functions, and then we generalized to schemes and maps of schemes and modules over schemes and all those things last time. So now we are ready to do cohomology. So let's look at some standard derived functors. So first of all, let's just quickly recall what are the things we have in hand. So if X is a topological space and OX is a sheaf of rings, mod OX is the abelian category of OX modules. Then we saw last time that every OX module embeds and admits an embedding into an injective mod OX injective module. So similarly, one can show that, not similarly, but okay, I mean, it's not very difficult also to show that every OX module admits a surjection from a flat module. So what you have to do is locally go over section, over each open set, you find a section, and then corresponding to that section, you can come up with a flat sheaf which maps onto that section. So essentially some kind of extension by zero. I mean, you can do it locally over that open set, but then you can extend that sheaf by zero, and that will also be a flat sheaf. So you can look up these things. And so if you can do this for one section, then you just take a direct sum of such sheaves over all possible sections over all possible open sets of M, and then you get your flat surjection. Such sheaves are rarely quasi-coherent, but that's okay for various purposes. What is unfortunately not true, which is unlike the case of rings, is that there are enough. I mean, there aren't usually enough projectives. So that is the one thing which we try not to use. I mean, because we don't really have it. So. And so once we have these, then we can certainly take more generally, not just embed it into an injective or surject from a flat module. We can in fact extend it to resolutions. So take the co-kernel and then again embed that into injective, so on and so forth. So that gives you an injective resolution. And similarly, in the other direction, you can get a flat resolution for a single module. So once we have that, then we can have various derived functors on I mean, here right now, actually, it's what is called as a ringed space. So I'm not really assuming it's a scheme in some sense. Here we can also compute derived functors on such a ringed space. So this is just a notation. So if we come, this HIXM, where M, okay, I forgot to say M and N are OX modules. So HIXM is the ith homology of group homology of this complex of groups, which is, or if you like, a complex of OXX modules. So these are modules over the global ring. So the global ring is a ring of sections of OX. And so you just apply gamma X to an injective resolution of M. And similarly, I mean, these are the standard ones. So this is the only, I just need to mention the differences. So here, this is sheaf X, and this is the global X. So this means that I'm applying sheaf hom here, and the net result is, again, a complex of sheaves. So again, I'm replacing N by an injective resolution and then applying hom of M. So I hope you're all familiar with the general principles behind computing this. So these are all, in this case, since gamma is a left exact functor, I will be only interested in the right derived cohomologies of this. So therefore, I will be taking injective resolutions. And similarly here, if you fix M, then this is left exact here, and so we'll again take its right derived functors. So you take injective resolutions, and then apply sheaf hom. So the net result is again a sheaf, and then you apply HI, and here I put an underline to emphasize that I'm taking the homology as a sheaf. So I mean, this is a complex of sheaves, and then I take the homology. So that will again be a sheaf, and that's the sheaf coming from the ith spot. So that is your sheaf Xi. Global Xi, you just take global homs. So these are just sheaf homomorphisms from M to J dot, and that's again a complex of abelian groups and take its homology. Similarly, you have TOR. So you just take the tensor product and then look at the global section. Compute the sheaf homology. So simply take the homology, and that homology as you take in an abelian category. In the abelian category of OX modules, you take the homology. Finally, if you have a map between two topological spaces, then what you do is you given a module M here and a module N here, you can try to push this down here and push that down, pull this back up here. And corresponding to that, you have your corresponding derived functors. So for example, if you try to push it down, that is F lower star, and then there are Ri, so the right derived functors of, because F lower star is again a left exact functor. So you have its right derived, so you take its right derived functors. So this is Ri F lower star, and by definition, this is Hi of F lower star of the injective resolutions of M, and similarly for N, you have F upper star of the flat resolution of N. So you have to take a flat resolution and then do it. Okay, it turns out, okay, injectives are good, but sometimes you need a little bit something else. So that also comes in handy, but I mean, I'm not sure I really needed it today because I'm going to skip certain things. So, but when I initially planned, I had this in mind. So let's see, anyway, I'll go over it since it's written up. So sheaf is called flask, or sometimes called flabby, if basically the restriction maps are all surjective, and for that it's enough to assume that the first open set is your the total space, and from here to any other open set, if you assume it's surjective, then you can also take any intermediate open set, and again that will also be surjective. So it means, or put another way, a section here lifts to a section here, or from any open set to this. So these modules are, I mean, okay, you have to look for them a little bit, but typically they turn out to be somewhat big. I mean, if you just take in algebraic geometry, if you just start with an arbitrary module, it's very unlikely to be flask. But the good thing, or the useful thing, is that injective modules are flask. So this is it's not very difficult to show from the basic properties of injective modules, and that says that, okay, I mean, this is somewhat large class because we can easily construct a lot of injective modules. Here's another interesting example. On a topological space, take this sheaf of singular cochains that I found 2 lectures ago, or maybe it was last lecture, I don't remember. So you have to look at singular cochains on every open set and maybe sheafify that pre-sheaf. And so even if you don't sheafify it, it's actually flask. So that will be a pre-sheaf, and that is flask basically because your singular chains and singular cochains complexes from open set to the larger thing, they split off because these are all I mean, free modules over a certain basis. Over smaller open sets, they are free modules over smaller bases and singular chains, and then you are dualizing it, and so you can easily show that this is flask. So the property of flask sheaves that makes it important from the point of view of cohomology is the following, which is basically that they are acyclic for cohomology, and that really comes from these 2 properties that I have highlighted here, which is that if you have an exact sequence, then if the first one is flask, then it turns out that the map of global sections is surjective. It's in fact exact. We know that the map of global sections for any such short exact sequence of sheaves is always left exact. The problem is on exactness on the right, and that is what we saw even for I mean the exponential sequence and for various other sequences. That is the that's the one which actually is the principal cause of cohomology here. And so flask sheaves work well in that regard. And so if these 2 are flask, then the third one also turns out to be flask. And So this is kind of useful because it allows you to prove this property, which is that if F is Flask, then its higher cohomologies all vanish. And so they are effective, they are very good replacements for computing, cohomology of the global sections functor. Instead of looking at injective resolutions, you could also look at Flask resolutions. And that's useful in certain contexts because you can, you might start with injectives and do some operations on them, and then they may not be any more injective, but they often turn out to be Flask. So this is somewhat useful enlargement of the category of injective modules to Flask modules. Okay, and what I need to next, so here it is. The next thing is take a closed subset of a topological space and let U be the complement. So that's an open subset. And let J be the inclusion map from U to X. Then you can look at, I forgot to write the name for this. This is called cohomology with supports. If you have not seen it before. So this is just saying that for any V, instead of looking at all the sections of F over V, you look at only those sections whose support is inside the closed set Z. And let me remind you, so that is just the stock of S at X is 0. So take the image of S in the stock. So there's a natural map from FV to the stock, and take the image of S there. That should be 0 for X not in Z. So therefore, if at all it is non-zero anywhere, that those points lie in Z only. So that's the support. So the definition of support is all those points where Sx is not 0. And so we are saying support is completely inside Z. So we are looking at only a subgroup of the set of all sections here. And so therefore, what you get is a subsheaf, sub-presheaf, but in fact, it turns out to be a subsheaf. So that's very easily seen just from the definition. And so this has produced, we have produced a subsheaf here. And the subsheaf has a property that all its sections are now supported. Their support lies inside this closed set Z. Here Z may not be inside V, but that's okay. So support is inside Z. That's all it matters. So if V is, Z doesn't lie inside V, then you have to just look at Z intersection V. But anyway, this statement takes care of everything. So the basic fact is that applying gamma Z like this to a Flask sheaf retains it as retains its Flaskness property. In particular, if you apply it to an injective sheaf, you may not get an injective sheaf here, but you will definitely get a Flask sheaf, and that is good enough for various calculations. So the useful thing about, so here's one thing that is, here are a couple of important exact sequences associated to a closed set. So first thing is, if you have a Flask sheaf, then, so if F is not Flask, then you have exactness till here. And if you have a Flask sheaf, then you have exactness everywhere. And this exactness is the following. It's saying that gamma ZF supported, so sheaf with sections in Z, support in Z, section supported in Z, is a subsheaf of F that we already know. And what it's saying is that and then this is, what is this? This is, you restrict F to the open set U, and then you push it forward, J lower star. So let's go back here. This J was this inclusion map. So by restricting F to U, so we sometimes write it as J upper star. And so that is the restriction of F to U, and then you push it back here. And so therefore, you'll get J lower star F of restricted to U. So you started with F restricted and push it back. So you get something here. And there's a natural map from here to here. Its kernel, you can see any section which is supported on Z will go to 0 here, because in some sense, that's easy to say, because support lies in the complement of U. So one can see that. But yeah, so this you can see. And the exactness here, however, depends on this last exactness, however, depends on F being Flask. So now if you use, so therefore, if you take the higher derived functors of gamma Z, what you get is for this sheaf G, you get, so write down the long exact sequence. And so initially you get, this is the zeroth, the zeroth derived functor of gamma Z. Since gamma Z is left exact, its zeroth derived functor is itself. And this is the identity functor. So you'll get G, and then you'll get this again itself. And from here, you'll get the first one in the long exact sequence. And then keep in mind that essentially, if in terms of functors, here we have applied the identity functor. For F, we are just putting F here. So its higher derived functors are all 0. And so therefore, after that, the higher derived functors of this and the next one here, they become, oops, so there's a mistake here. Should be +1. Okay, so the higher derived functors of this become isomorphic to the next one, and then the the identity functor, all the derived functors are 0, so they don't play any role. So only the 0th one is itself, and then after that there's nothing. So this is what we get here. And similarly, now instead of doing this, we take its global sections, and then it turns out this is also exact, and I have 0 gamma z x f. So what are these? These are, okay, maybe I have not defined this, but you can guess what it is. So these are all global sections of f which are supported in z, and these are all the global sections of f, and these are the sections of f over u. And again, you can see that clearly it's exact till here, because anything which is supported on z has no support in u. U is the complement, and then because f is flask, this is also surjective. So you can see that this is an exact sequence, but in fact what you have is not just this, but so this is for a flask sheaf. Again, f was a flask sheaf here, and for an arbitrary sheaf G, you have this long exact sequence. So take the derived functors, and now, however, you are looking at derived functors of the global sections functor. Global sections functor is not exact, so it will have higher cohomologies, and so therefore you will now get a long exact sequence where nothing collapses. So gamma u g, and then h1 and h1 and so on and so forth. Okay, so these are the two long exact sequences associated to a closed set in a topological space X. Next, I'm going to look at cohomology over affine schemes. So again, I'm just going to, this we're going to go really fast. So what's special about affine schemes? These are in some sense the smallest, I mean, open sets. I mean, the smallest open sets that one usually writes down are these affine schemes. I mean, these are the smaller ones. And the larger ones will be like the projective, or what are called as proper varieties. So we'll come to that. It's smaller in the sense of trying to embed things inside as an open subset inside bigger schemes. So you'll always find, I mean, the affine schemes form a base of your affine open sets form a base of your topology, basis of your topology, etc. So the interesting result is that over affine schemes, there's pretty much no cohomology for quasi-coherent modules. So let X be a affine scheme, and for simplicity, we'll assume Noetherian. It's known to be true without Noetherian hypothesis, but proof is much harder. So then if you take a quasi-coherent OX module, then its higher cohomologies are all 0. 0th cohomology will, I forgot to mention, 0th cohomology is just M itself. So okay, what is M? Okay, so that needs to be said here. So we'll see from the proof that the 0th cohomology will have to be what it has to be in a given situation. So I'm only going to give a sketch proof of this, because actually there are some subtle technicalities hidden in this based on what we have defined. So sketch proof is that first, the way we defined quasi-coherent OX module, we didn't really assume everything was of the form M tilde. This was certainly one example of quasi-coherent, but what we assumed was that it's you can find an open cover over which it is of the form M tilde, open affine cover over which it is of the form M tilde. So it could presumably happen that over X equal to spec A, you can find an open cover over which you can write it as M tilde, but we don't know what is happening globally. So as it turns out, that's not the case. In fact, globally also, every quasi-coherent module can be written as M tilde. This needs proof, and I'll skip that. And once we have that, then take an injective resolution of M over just the ring A itself and apply tilde, and hope that this gives you a good way of measuring cohomology. So what happens? So since tilde is an exact functor, when we apply tilde, it turns out, because this is an this is a resolution, the exactness will tell you that this is also a resolution. And so I have a resolution here, but what kind of resolution is it? So it turns out that in fact, these I tildes are, I mean, one can easily show they are Flask. Easily means you need a little bit of argument from using the fact that this consists of injective modules, but in fact, one can show that they are also injective in the category of OX modules. So in fact, you get a OX injective resolution. So this is exactly the kind of resolution you need to measure cohomology. And so you just measure the cohomology. So you apply global sections functor to this one, to this, to this resolution. And so what you get is hi gamma x of I dot tilde. But gamma of m tilde is m itself. I mean, that's the way we defined it. So gamma of I tilde is I itself. And I mean, this is something that was implicit in the way I said it. So therefore, this will turn out that it will turn out that we have hi of this. So if you apply gamma x of I dot tilde, you just get I dot. And so you're just looking at hi of I dot, but I dot had only one homology m. So that also shows you that h naught of I dot is m. So that's the sheaf that you, that's the module corresponding to the sheaf that you started with, quasi-coherent sheaf that you started with. So, so that's it. That shows that over affine schemes, there are pretty much, I mean, this whole homology business for quasi-coherent sheaves really just degenerates into nothing. I mean, just the global sections, and there's nothing higher than that. That's no longer the case for other schemes, obviously. Otherwise, we won't have any cohomology, interesting cohomology theory. Also, this is a small technical point, but keep in mind that this was only true for the global sections functor. If you take this supports functor, it's no longer true. The supports functor is actually, you can think of it as a composition of two functors. One is the global sections functor, and one is the gamma z, sheaf gamma z functor. And somehow the sheaf gamma z functor, I mean, that no longer has this this property that hi is 0 for I greater than equal to 1. Okay, so because affine schemes or affine varieties have no, I mean, not much of cohomology to offer, we can use a Mayer Vietoris like argument to compute cohomology in terms of affine cover. I mean, because that's what we do in Mayer Vietoris, we cover them by contractible open sets or open balls of Rn or whatever, and then we try to compute cohomology in terms of the combinatorics of that cover. So that's what we can do here also. And when you do that, that's called the check cohomology. So this is what you do. So let's start with X, any scheme, preferably Noetherian, because most of the results will be using R for Noetherian. So, and take any open cover. It doesn't have to be finite, but yeah, I mean, right. In fact, I have been loose here. So just take an open cover here. We'll call it U. For simplicity, if you want, you can assume it's finite. F sheaf on X. Then what we can, the check complex associated to this cover, so we'll call it as C dot U of F, is exactly like the gluing condition, but it's generalized to higher intersections. So start with F of UI over each open set and take the direct sum of all the sections. And then you want to see if you can, if they agree on overlaps. So look at F of UJ, I mean UI UJ, or I have written it here as UJ1, UJ2, where J1 less than J2, so that you're indexing all the intersections and you're looking at F over the intersections. And then you have these triple intersections, UK1, K2, K3. So this is by definition UK1 intersection UK2 intersection UK3, and so on and so forth. So you have all these, and these maps are, as you can imagine, they are essentially restriction maps with a plus or minus sign in front of them, and the minus sign essentially alternates depending on what is the extra index you have added. So basically, from a two-fold intersection, when you go to a three-fold intersection, you have added an index if at all that projection map exists. So if you have added an index, you just see where you have added, either in the left, middle, or right, and then accordingly you put plus, minus, plus, or something like that. So So these are just restriction maps with a appropriate plus or minus sign, and then you can see that this will give you a complex. Those are all straightforward calculations. So this is what is called as a check complex. More or less from the definition, we can see that the zeroth homology of this check complex will be the global sections, because those will be the sections over the open cover which agree on overlaps, because there's a minus sign here. I mean, one restriction is the standard one, the other one will be the minus of it. So you'll be sending, so an element which goes to 0 here will be something minus something. So that means they agree on overlaps. So H naught of this complex, I mean the zeroth homology here will give you the global sections, but the higher homologies of this complex are more complicated. So those will be called as a higher check homologies of F. So we'll define them like this. And the basic theorem is that take a Noetherian scheme and cover it by affine open sets. And a small technical condition here, which is that, and you can see where you will need it. You assume that finite intersections also have the property that they are also all affine. So in the check complex, all these open covers that you are going to get, you want all of them to be affine open sets. And if you make that assumption, which is true for a large class of schemes, so I'll say something about that shortly. Then for any quasi-coherent sheaf F on X, its derived functor global sections cohomology agrees with the check cohomology. And this turns out to be a very useful result, because we know how to calculate the check complex. We know, I mean, these are all affine. So in principle, these should be easy to calculate, because this is just, I mean, it's just some module over the corresponding affine ring. And so, yeah, it depends on how well we are able to calculate these, but yeah, quite often you can. So in fact, this is a very useful result. And because I mean, this is only a theoretical definition. In principle, it's this which is used for calculations. So I'm going to skip the proof of this theorem. Essentially, you have to use the fact that over affine there's no cohomology, but you'll also have to do a little bit more work and show that for Flask sheaves, again, this has no higher cohomologies and things like that. So it's not hard, but it needs a little bit of proof. So finally, what is this condition here? This condition here that the intersections of affines are also affine is quite often guaranteed if you assume X is, I should say, quote unquote, like a Hausdorff space. So I say quote unquote because in the Zariski topology, nothing is Hausdorff. So it is not in that sense. But if you imagine that X was a complex manifold, I mean, defined algebraically, by which I mean it was X was given, I mean, O is happening over complex numbers and it's defined using polynomial equations, etc. Then this condition is guaranteed if we assume X is Hausdorff in that sense, because you can remember X is no longer affine or projective. It could be slightly more general. So you could obtain X by gluing things. And if you glue things, then we know, even in the case of manifolds, you can get non-Hausdorff spaces. So you want to avoid those things. And once you've figured out the technical condition for avoiding these things, then this condition automatically follows. So it's called separatedness. So this is what is called a separatedness in scheme theory, but I'll not mention it further. Okay, let's move on. And this is probably the last thing I've written on the, yeah, that's it. And so now I have to start writing live as I go here. So we'll now compute cohomology on Pn. And well, not compute it, but just say what it means to compute cohomology on Pn. Oops, I did something here. Okay. So let's start with your polynomial ring, and X is projective space, and take a module. And let's, for simplicity, start with a module of this type, M tilde. I mean, this is your, in fact, one can show that, I mean, this is pretty much every quasi-coherent module looks like this, but we will not prove that. So we are looking at an arbitrary quasi-coherent module. And the question is, what does it mean to calculate this? So I'll just unravel the definition. But there's one thing which comes in handy when we try to compute this, which is that while computing this, it turns out You can also compute the, simultaneously the compute, or you can, the same process will also give you the cohomology of the various twists of M tilde. So let me write it out. What will it mean? So what will it mean to calculate the cohomology of this? So here, unfortunately, I have used the same letter X as X1 to Xn. So I hope that doesn't cause confusion. So what it would mean is the following. What we'll do is we'll use a check covering of projective space. What is a check covering of projective space? The check covering of projective space is where each of these xi's is not zero. So x1 not equal to 0 will give you an affine open. By check covering, covering by affine opens, whose intersections are also affine. So for example, if you put x1 not equal to 0, that will give you an affine open cover, and similarly x2 not equal to 0 up to xn+1 not equal to 0. So then if you try to calculate it, you'll see that what you're really calculating is, so the corresponding check resolution will turn out to be, so let ui, let u is equal to, so this ui, where ui is the locus where xi is not equal to 0. So this is my open cover, and with corresponding to this open cover, the complex that I'll be writing down is the following. So I look at M. So what is M tilde? On this open cover ui, M tilde is nothing but the degree 0 part of mxi. The degree 0 part, only the degree 0 part. So I'm supposed to actually put a bracket here. That will correspond to the degree 0 part of mxi. But remember, I have therefore, I have in fact tried to take care of all the shifts. And when you try to take care of all the shifts, then in fact you can drop these terms. And so if you are trying to compute, so therefore what I'm saying is that if you are computing the cohomology of G, you can just start with mxi. So this will be my first term. So what I'm trying to calculate is the check cohomology of G. So this is a check complex of G, and this will be the following. So I put a direct sum here over I. And then the next one will, so what is the intersection of two such open sets? So it's xi not equal to 0 and xj not equal to 0. So if you think about it, you will get exactly xi, xj. Or maybe I should call it x, let's see, j1, x j2, and j1 less than j2, and so on and so forth. So the next one will be like this, and it will keep on till the last one, which is n+1 fold intersection. And so the last term is m, there's only one intersection there, and so that's mx1 up to xn+1. So this is the complex, okay, sorry. Yeah. So this is the complex that I need to use. This is the check complex that I'll get for calculating the cohomology of G, which simultaneously takes care of all the shifts of F, which is M tilde here. So, so this is the recipe. And so if you use this recipe, you can, so you can certainly see, for example, that M0 is sitting inside, M is sitting inside here. And similarly, but there are higher cohomologies here. So now I want to mention something, that what we have written down, this complex is also, so yeah, this is also the, this is also the check complex but not for G, but for M. So let's just say M or M tilde. So let me first say check complex, but on a different space, on An+1. Here, the tilde is with respect to an+1. So, okay, not quite. So m tilde restricted to n+1. So here m tilde, this tilde is with respect to an. So the tilde symbol was being abused. I mean, we could use it for affine schemes as well as for projective schemes, for graded modules as well as for modules over a ring. So this is m tilde with respect to an. So if you do this, then you'll see that an+1 minus 0 also has a similar open affine cover. Again, same kind, xi not equal to 0, except that that affine cover is has one dimension higher than the affine cover of projective space. Projective space is one dimension lower, and projective space is quotient of this. So it's a one dimension higher one. And therefore, but here we are not doing it for G, here we are doing it for M itself.
Suresh, this is m tilde on an+1, right?
Oh, sorry, n+1, thank you. Yeah. And therefore, if you go through the local cohomology sequence that we wrote some time back, this will tell us that, and hence, anyway, maybe I should cut a long story short. So anyway, so what is the conclusion I get from this is that, let's see, what I want to say is, yeah, this complex measures the, so therefore it's this complex is almost, so this is hence it almost measures, well, one can make it precise what it's measuring, the homology of so first of all, okay, right, so this is let's call this as let's give this a name, so let's call this U inside an+1, and it measures gamma m. So this is the maximal ideal. So maybe I should rewrite it like this. Gamma m of m tilde if you like, or an+1. Well, so this is so how do I quantify what do I mean by almost measures? Essentially, you just use the fact that what we are, this is the check complex of the open cover U. So what it really measures is what it's really measuring is gamma U. Hi gamma U of m tilde. And so the question is, sorry, hi. Yeah. So what is the relation between these two? But we have already said what the relation between these two is. This is your maximal ideal. Here m is the maximal ideal corresponding to x1 to xn+1, and this is just notation for saying I'm looking at. Okay, so first of all, when I write gamma m, I mean the gamma of the point m in your affine scheme. So therefore, that's a complement of U. That's the origin. So this is just the origin in. Oops, I used the wrong thing. So this was M. That's just the origin in your an+1, and that's a complement of U. And so we saw that this cohomology is related to this cohomology, and that is just a few slides above. We saw that. I mean, just there's a difference in the indices. So this one is isomorphic to. So this one is isomorphic to this one. I mean, so you can put chi+1 and hi. So these two are isomorphic for I greater than 1. These two are isomorphic for I greater than 1. Anyway, so finally, what it means is that this tells us that one can use various considerations to make this calculation. Oops, I seem to be using the wrong. Sorry. To make various we can use various methods to calculate these, and that allows you to calculate this. So for example, coming back to the situation here, in the case of polynomial ring, you can use the fact that this is a regular ring and this is a regular sequence here. And that will tell you that if, for example, M is the ring itself, then in fact, there should be no cohomology except in the degree 0 part. The degree 0 part should have cohomology R. And here you will have cohomology. So the net conclusion will be that the following. So I will just cut a long story short. So finally, thus, HI of, so what we get is, sorry, H0 X of OX n is isomorphic to Rn, the nth degree part. So this is degree n monomials. So here, okay, I made a slight abuse of notation. I pretended that K was a field. I said something is regular. That is if you assume K is regular. K is A is a field. So if A is not a field, but still you can use similar arguments and argue that. So let me just pretend that A was a field there. And so Rn is degree n monomials. And then this is H0, then H1, and in fact Hi X. So this n should be replaced by m, sorry, because that is not the dimension of the Hi or X OX of, let's see, anything m is 0 for I between 0 and n. And then maybe I should enlarge it. That will make the handwriting a little better. So that's what I usually do. So then Hn of x of OX of minus n minus 1. This is again is equal to A. And then finally, so this part is follows easily from all the all this follows from the fact that if you go back to this complex here, and if if you pretend, for example, if K is a field and so it's a regular ring, then there is no homology except for R here, and then in the last spot here. So using that fact, we see that there is no homology in the middle. Zeroth homology is again will just give you this is Rm, this m is just the degree m part. And the last one, in fact, one can also show that there is a pairing. So the pairing is that Hi, so there exists a pairing Hi X. So this needs a little bit of calculation, which I'll skip. So Hi X OX of maybe m cross H. Okay, so I think I'm writing too big. Sorry, I'll just write. Sorry, not Hi, H0. And Hn X OX. And then I'll just do the minus of that. So minus n minus 1 minus m. And then there's a natural pairing from here to Hn X. Same thing, OX minus n minus 1 to A. So this is isomorphic to A from the part on here. And so this is a perfect pairing. Okay, so this is what we get by some explicit calculations. The important thing to keep in mind here is that OX minus n minus 1 we calculated was actually omega n of PNA. So therefore, what we have, so this is the first glimpse of Serre duality. What we have here is that the top cohomology of the cotangent, the top exterior power of the cotangent bundle is, I mean, so if you assume you are working over a field, then it's, I mean, let's assume algebraically closed field, then you'll get K is K. And then for all other, well, right now, not all other, but for certain class of coherent sheaves, so these are coherent sheaves of the type OXM, you have this kind of a pairing. So this brings me to the second part of the talk, but actually there's not much time. So I'll just very briefly say the second part of the talk will be, I'll just get started with Serre duality and then I'll elaborate on it next time. So here's the, so let's, okay. This is part B. And this will talk about Serre duality. Okay, so here's the statement that I want to give. So the statement is that, so there are various forms in which a statement comes. So here's so this is the first form, so first version. So X projective over a field K. And then what we have is HI X, and maybe we can put some, let's see, yeah, so okay, so right now I'll need one more assumption. We'll assume that suppose X is, assume X is smooth over K. So smooth definition, one has to be a bit careful if K is not algebraically closed. So right now, let me just assume K is K bar, but in fact, I'm not going to elaborate more about smoothness anyway later on, but still, just to be complete for this lecture, let's assume K is algebraically closed. So then X is smooth over K. And if X is smooth over K, and this is, this will have a certain dimension. So of dimension N, then HIX E, so where E is a locally free sheaf, but in fact we will soon replace it by any coherent sheaf. So this is isomorphic to, so this is again the cohomology of E with over X is isomorphic to Hn-I. Okay, I think again I'm writing too big, so maybe I should, okay, just a minute. Hn-I X, and then you dualize E, and then look at nth omega. Okay, so that's, I think that's what it is. Yeah. So this is the statement of Serre duality for any projective scheme or variety over a field, algebraically closed field, which you assume is smooth of dimension n, then over that field, then we have, so this star here is the vector space dual, and this is the sheaf dual of E. So dualize E with respect to OX. That is the, so this is a dual sheaf. This is tensoring over OX, and this is the, so one can show that the module of differentials has a rank n, is a rank n free sheaf, locally free sheaf over X, and so you can take its nth exterior power. So you take the nth exterior power of that, and then so we are saying that the ith cohomology here is isomorphic to the n minus ith cohomology here. So this is the statement by which I think this is close to the original form in which Sayre proved it. So I guess how much time do I have? Can I take a few minutes?
Yeah, you're done with 15 minutes, but you can take a few.
Okay, I'll just take a few minutes. So first thing I want to mention is that if you look at the statement, if you put, let's see, yeah, if you put x is equal to O, so sorry, E. So putting E is equal to O tells you that, so in particular, so what are the various things that this formula seems to suggest? So this is, of course, something that you will, that doesn't, it's not that it comes out of the formula, it's something you established much before. So it's part of the thing that that is hidden in this equation, is that if you put E is equal to O, it is telling us that Hn of x of omega nx is isomorphic to, and so I put I is equal to 0 and E is equal to O. And so therefore that's isomorphic to H0 of XOX star. Sorry, my connection went off. Where am I? Okay, yeah. So I'll just take 2 minutes and I'll stop. Sorry.
You need to share your screen again.
Yeah, I'm trying that. So mirror, zoom. Oh, okay, sorry. Yeah. So among other things, this theorem, this first version is telling us that the nth cohomology of the cotangent nth top exterior power of the cotangent bundle is K. And that is what we had, if you go back here, that is what we had for projective space also. Where was it? This one here. The nth cohomology is here. I did it over the arbitrary ring A, but it's basically this was the cotangent bundle and the nth cohomology is A. So for projective space, we have that. And in fact, for projective space, we have this statement is also is exactly that Sayre duality statement. This is a perfect pairing. If you look at it for 0 to n. Except that it's not for all possible coherent sheaves, for only coherent sheaves of the type OXM, where M is an arbitrary integer. But it turns out that you can resolve any coherent sheaf by quotients of, I mean, you can map for some suitable M, suitable negative M. You can map any sheaf, any quasi-coherent sheaf coherent sheaf. You can map a direct sum of various copies of this, and that will allow using using a resolution of f by that sufficiently long resolution, you can in fact show that you have the same kind of pairing for any coherent sheaf f here. So that will allow us, in fact, to prove that prove the statement for projective space. So for projective space, this essentially is nothing but a little bit of chasing here and there, and these explicit calculations. These explicit calculations, together with a little bit of chasing, which I'm going to skip, will give us this theorem for projective spaces. But the question for just x is equal to Pn. But the question is, how do you prove it for other spaces? And then how do you generalize it? What if x is not smooth? What if x is not projective? What kind of statements do you expect here? So that's what I actually plan to talk about today. But I think I ran out of time in getting my notes written up. And then I think live writing is much, much slower. So I think it's pointless for me to start with anything new here. So perhaps I should stop. So maybe just one phrase I'll write and then I'll stop here. So one thing that helps us change this is to realize that in fact this is nothing but, so I made this assumption that I didn't say, so E was actually locally free here. And this is the form in which it looks like a good, nice duality statement, because there's I, n minus I, and E is also floating around there just like that. And this is hi, and this is h minus I, n minus I. But it turns out that the right version for this is to actually realize that this is nothing but Xed, sorry, not sheaf Xed, but group Xed. N minus I over OX. And then I'll bring this E dual from here to here. So E, then omega nx. So this is one small simplification I will do. So this is not hard to show. Basically, there is locally free, and so it's locally you can, sorry, yeah, yeah, that's right. So it's locally free is all I need, and then I can just bring it here. And so one can show that these two are isomorphic. So it is this version which actually allows us to generalize things a little bit. But to do that, we will have to get into the derived category. And also, we will see later that this here is, I mean, if you want to work with singular objects, then you cannot afford to work with omega n. So you'll have to replace this by something else. And finally, what is this whole statement here? So all these will become clear once we start working with derived categories. And that's what I will do next time. I was hoping to do a little bit today, but we'll stop here. Thank you.
Thanks, Suresh. Very much out of time, but if there's a very quick question, maybe we can have one.
Yeah.
Okay, and so far. So then we'll take a quick break and be back at 6:05.
Okay.
Any questions can be taken up during discussion.
Yeah, sure.